Hello, welcome back everyone. Let me hand the mic to Alastair, who will present the next session.
Hello everyone. So we have a session of two halves coming up now, so we've got a couple of talks taking place next. Then we have a break for a poster session followed by some coffee, and then we return at 4 o'clock here for the last two talks. Closer. Okay, so the first talk we have today in this session is SSH It by Sebastian Neef. Sebastian, would you like to start us off?
All right, thank you very much for the brief introduction. I'm Sebastian Neef, being a research assistant and PhD candidate at the Chair of Security and Telecommunications at the Technical University in Berlin. And I need to figure out which button to press. I believe this one? Nope. The green one. I'm pushing the green button, nothing happens. Nope. Can you help me, please? Oh. Yeah, I pushed it now. Oh. All right, weird. All right, so let's get started. I know you're all a bit sleepy due to the lunch, so I hope my topic is a little bit easier to digest. Let's start with the motivation. So, you all probably know SSH, the Secure Shell Protocol, which is widely used to connect to remote systems. And yeah, anecdotal evidence suggested that many users are not doing proper host key verification because they're either not aware of any potential security risk that it embodies, or they are just lazy. So an incomplete or incorrect verification could lead to serious security risks. Now it works, great. If the monitor could work as well, that would be great too. So yeah, there are SSH-FP records that were standardized in 2006, so that is more than 15 years ago. And that is one solution to the trust on first use problem that the SSH protocol has. However, since then, little research has been done on the topic. The only measurement that I could find in related work was done by Gasser et al. In 2014. So it's almost a decade later, and I thought, okay, we can do another measurement and see if that solution is now more adopted or not. So the contributions of the paper, which I wrote with my colleague Niels Visio, are the answers to the following questions. How common are DNS-based host key verification records? Do the SSH-FP records match their service counterparts? So obviously we have the DNS and the SSH service, and if those fingerprints do not match, we can do not do the validation. And then the last question is, are these records securely transferred using DNSSEC? Because if that path is not secured, then we'll see on the next slide that the man in the attack will move from the SSH level to the DNS level. And obviously, we publish all the artifacts that we collected during our research, so all the code will be online, all the intermediate datasets will be online to facilitate further research in the future, maybe to repeat such a measurement and draw some conclusions from new numbers. And we also produced a SSHFP Python library which complements other DNS Python libraries. So why do we need host key verification? SSH uses public key cryptography. So it uses that to establish the authenticity of the servers. So when you connect to a server that you have not connected to before, you will get the prompt that you can see below. And it says the authenticity of the host cannot be established. This is the fingerprint. Now you have to decide whether that is the correct fingerprint or if it's not. And this is due to the trust on first use principle. So many users which want to get the work done would just type yes and continue. But this is some serious security implications. So in short, the user should verify that he's connecting to the correct server, because otherwise an adversary that's performing a malice in the middle attack could obtain the login credentials or hijack sessions. So that's why this little tiny step is pretty crucial in the whole SSH ecosystem. So there are 3 ways to perform that host-key verification. The one that we just saw is a manual way. So in theory, the user would need to ask the administrator to obtain the fingerprint, then compare both fingerprints and decide if they match. However, we humans are kind of bad at verifying and comparing long, random-looking strings. So this has potential for human error. And also, we users are mostly lazy, and we do not want to contact administrators that we might not know. So another solution to solve that problem would be to use a certificate authority. So in that case, the administrator deploys a root CA to all the user's devices and then signs the host keys using that root CA, so that the user, when they connect, the SSH client can use the deployed root CA to verify the signatures on those host keys and decide if the fingerprints match. But still, this requires prior work. So the user has to go somewhere, the administrator has to deploy the root CA, and again, this might not work in all scenarios. So one solution where neither the user nor the administrator need to know each other, or there's no need for them to interact, are DNS records, so the domain name system. And there's an RFC that specifies SSH-FP records as a solution for that. So the administrator can publish those SSH fingerprints into the DNS, secure those records using DNSSEC, and then the user in its SSH client can fetch those records and use that for comparison, which is a pretty neat solution, in my opinion. So how does those records look like? They were standardized in RFC 4255, and then there were some subsequent RFCs that extended the algorithms that could be used for those records. So basically, we have the following format. We have SSH-FP, then the numerical value of the key algorithm, which is, for example, 1 for RSA, 2 for DSA, 3 for ECDSA, etc. Then we have the numerical value for the hash type, which is 1 for SHA-1 or 2 for SHA-256. And in the end, the third field is the hexadecimal fingerprint of the host key. So let's have a look at some real-world example. You can use any tool to query those records. And with the opendev.org domain, we can see they have 6 different records that are being returned. You can see in the second column that they have RSA host keys, ECDSA host keys, ED 25519 keys. And for each key type, they have hashed the fingerprint with SHA-1 and SHA-256. So now, how can we use that to connect to that server without having to answer the prompt manually? We have to pass the option -o verify host key DNS equals yes or ask to OpenSSH, because this is an option that is not enabled by default, unfortunately. And then SSH will fetch those records. As you can see in the debug output, it will find those 6 secure fingerprints in the DNS and then compare them to the obtained server host key and decide, oh, well, they match, we can continue with the connection. So there's no user interaction needed, which is pretty nice. So now that you know how that is supposed to work and that it's already implemented and could be used in the real world, we can now talk about the methodology, how we established what the adoption of that technique is. So for that, we built a little scanning system that first queries a domain that we input for those SSHFP records and validates their format. Then it follows up with a query for IP addresses for that domain so we can find potential hosts that might be running SSH, and we obtain all the different server-side fingerprints using SSH-keyscan. In the third step, we can now resend the SSHFP query to check if those records are transferred using DNSSEC, so security transferred. And then in the fourth step, we can do the comparison between the DNS-based fingerprints and the server-side fingerprints, because in the end, we need to know if there's a match between them or not. So how did we analyze our data? We empirically collected the data from two domain sets. The first one was the Tranco 1 million list. However, we got extremely few results back from that, so we decided, okay, maybe we can have a larger data set by looking more into the internet. And we did that through the certificate transparency log, which we monitored for over 26 days to obtain more than 515 million domains that we scanned for those records. So with that data, we did some quantitative analysis to answer all our research questions, and we had a good focus on reproducibility. So, as I said before, we publish all the code in intermediate data sets to facilitate future research. So what results did we get? So out of those 1 million Tranco domains, only 105 domains had SSHFP records, which is not a lot. Then, after scanning for those IP addresses, we found 75 SSH servers mapping back to 72 domains, which provided around 380 fingerprints that we could compare. So after the comparison, 66 hosts had at least one matching fingerprint. So DNS, server-side, at least one match. And then, mapping back those matching hosts to their domains, we find that only 28 are DNSSEC secured. So according to the standard, if you would like to use SSHFP records, you have to security transport them. So only 28 domains are applying the standard correctly. So let's have a look at the bigger picture. So for the certificate transparency log, we obtained 550 million domains, of which 136 million were unique domains. So I'm not sure if everybody can read it down here. So a unique domain would be www.example.com and mail.example.com, because both can point to different servers, of which one might have SSH and the other one wouldn't. And then we have registrable domains, which would be example.com. So out of those domains, we find 23,800 unique SSHFP records mapped from 74,000 record sets, of which only 6,000 were unique. And those record sets mapped to 70,600 unique domains, of which 7,000 were registrable. Again, we query for IP addresses to obtain potential SSH servers. We find 16,300 of them, mapping to 11,500 unique domains. And in total, we have 72,015 server-side fingerprints that we could analyze for the matching process. With that, we find 14,500 hosts with at least one fingerprint that map back to around 90% of those 11,500 domains, so 10,300. And again, the amount of domains that use DNSSEC and SSHFP records is quite low, so only 3,800 unique domains use DNSSEC. So what does it mean for being able to do or use that to validate the fingerprints? Newer versions of SSH implemented a bug fix for downgrade attacks and now require that the full set of SSHFP records matches the full set of server-side records. So you need a 100% matching ratio between DNS and server-side records. And from our data set, we find that less than 50% of the hosts fulfill this criteria. So although one could argue that the standard requires only at least one match, the current OpenSSH versions implement it in a different way. So again, we can see for Tranquil 1 million, we have 36 hosts, 84% with a 100% match. And then for the certificate transparency, we have only 23.6% of 100% matching rate. And the others are kind of in between. So this could be either to changing host keys on the server and not updating the DNS records, or forgetting to rotate the DNS records or the server-side keys. So from a security perspective, we can have another look at the DNSSEC usage. And now we see in the bar plot on the left side that we have over 50% of these SSHFP records that we analyzed deployed insecurely. So there's no DNSSEC, there's no protection, and that means that the malice in the middle attack could move from the SSH level to the DNS level, and there's no benefit in using SSHFP in that case. And almost the same number we get for bar plot B, where we look at the unique hosts and domains. And we can see with the dark gray bars that less than 50% of the matching records that we found are securely transmitted. So there's a lot of room for improvement. So what does it mean? Overall, the adoption of SSHFP records that we discovered is in the order of magnitude of 1 in 10,000 domains. Again, we believe that is due to it not being enabled in OpenSSH by default, and there's no hint for that feature. So there might be just a lack of awareness of that feature. Also, a dependency on secure DNS transport like DNSSEC might be an issue here, because DNSSEC is also fighting with low adoption rates and its own challenges. So the work by us and Gus et al. Can only provide a lower bound on that number. From a security and privacy perspective, we find a rather lower matching rate than Gus et al. So we had 88% of matching record between DNS and servers, and Gus et al. Had 94%. So we attribute that to the improper deployment that we have seen. So in some cases, the whole record doesn't match, but in others, there's only one field that is wrong, either a wrongly configured key or hash field, or the fingerprint value is not matching. However, on a positive note, we find a slight increase in DNSSEC adoption compared to Gus et al. So they had 31.8%, we have 44%. But this is over the course of the last 8 years. So with 44%, there are still a lot of records being insecurely transmitted, which is not good. What our data also shows is that modern key algorithms like elliptic curve and SHA-256 are still behind in numbers compared to the established algorithms like RSA, DSA, and SHA-1. And one further point that could be interesting from a privacy perspective are duplicate fingerprints. So either we can use that to find links between domains when the fingerprints or SSHFP records match, or we can find potential key reuse, for example, when two different SSHFP records match to different servers, but they have the same fingerprint. So obviously we face some limitations, and we also have some ideas for future work. So the limitation number one would be that we could only scan the public DNS and not look into private DNS servers or internal DNS servers. And in fact, I had some people from companies tell me that they use SSHFP internally, but they do not have that deployed in public. Another limitation that we faced were a large amount of resolving errors amounting up to 5% of our queries. So they were answered with NX domains or with timeouts, and we attribute that to some scanning instability or maybe authoritarian name servers that are misconfigured. And we had some short amounts of disconnects from the certificate transparency log provider that we used to obtain those domains, which is only up to 3% of the total time. So there might be some domains that could not be successfully scanned. But again, I'm currently looking into reliable DNS scanning, so I might be able to redo this scan in a couple of years, maybe in 5 or 10. Let's see. So for future work, one interesting point would be to find alternative and better domain sources. So we had the Tranco 1 million list, which didn't return a lot of results. We tried to compensate for that using the certificate transparency log, but still, this is like an open-ended scan, and we might not find all domains that might be using SSHFP. Further, a longitudinal study to monitor changes in the adoption or in the deployment of SSHFP records would be nice, to do like a scan once a day or once a week or once a month and then compare it over a longer amount of time. And from my personal perspective, what I would love to learn about would be causes for the low adoption of SSHFP. Is it just unawareness that nobody knows about that feature? Is it technical hurdles because of DNSSEC or the deployment deployment that needs to be done? Or is it something else? Because this feature exists for more than 15 years and still is not widely adopted. So, in conclusion, we can say that we performed a large-scale analysis of those SSHFP records. We find that there's still no widespread adoption of them, although its standardization was more than 15 years ago. We find a lot of misconfiguration that eliminates all the benefits that those record types promise. For example, when there's no match, we cannot do the validation and the user is forced to go back to manual verification. If there's no DNSSEC, then the secure transport isn't guaranteed. So the malice in the middle attack could happen at a different level, which also defeats the purpose of proper host key validation. However, if used correctly, the SSHFP records can mitigate many of those trust on first use risks that SSH currently has. So, in the end, I believe we all do great work on cryptography. We improve algorithms. We try to solve the problems. But if it doesn't get adopted by the wide masses, then there's no real benefits in the real world. And I believe this is something that we should aim for, like try to make our new and better algorithms more adopted in the wild, in the real world. And with that, thank you for your time and attention. Thank you for not sleeping. And now I'm open for questions in this talk.
Thanks, Sebastian. Okay, who's got some questions?
Hi, I have a question regarding SSHFP and the interaction with SSH clients, because if DNSSEC is not employed, are clients actually accepting the DNS record, or are they just discarding them?
That is an implementation detail that is still on my to-do list to check. I recall my co-author Niels commenting that OpenSSH did not properly verify if those records are securely transmitted. So there might be an issue as well. But if you recall the debug log that we saw, SSH said it found secure fingerprints in the DNS. So I would assume that it is checking the AD flag in the DNS response. But I would need to make sure it's really doing it. Good question, by the way.
Any other questions? So I had one about whether you looked at doing any port scanning to work out what proportion of the domains had SSH at all or not, and therefore could that be part of your calculation as to the proportion of SSH servers that were secure?
We scanned only the port 22, like the standard port, but we didn't really do a massive port scan that could have get us blacklisted or anything. And also we just queried the server for those fingerprints. So we didn't actually try to log in, which would show up in any intrusion detection system that could get us blocked. We just kindly asked the server, provide us your host keys and the fingerprints for them.
But you tried that just on the domain names you got back, rather than necessarily doing a full scan of a broader portion of, let's say, IPv4.
Yeah, exactly. We just did the SSH connectivity or fingerprint scan on those records or domains for which we found SSHFP records and found valid AP addresses. So to reduce the total set, yeah.
Other questions? Okay, let's thank Sebastian once more. Thank you, Sebastian.
Thank you so much.